from the University of Birmingham, and first of all I'd like to thank the organisers for inviting me here. It's an amazing campus. I'm going to speak to you about we heard in the very first talk about some of the systematic effects and noise sources that make Casimir force experiments so difficult. I'm going to present potentially entirely new technology that hopes to circumvent some of those problems, brings a lot of its own problems. Let's see whether it works. So this picture here is essentially, it doesn't look like it's also noise, but I'll try and explain why it works like one. So the background is this has come from, essentially as a spin-off from a short-range gravity experiment, and a lot of people here pick on that sort of thing as well. So it's the inverse square law experiment. It's aiming to measure gravity in a range of sort of around 15 microns. But it's the device we've built to do that can easily be adapted as a platform, sort of literally and figuratively, for any short-range weak force measurements. So I'm going to talk about, first of all, the design of that experiment, the triangular superconducting torsion bonds that you saw at the start, and then describe the readout, the mass design, how we would adapt that to make a Casimir force experiment, and the other parts of the experiment, the micro-precision system. So we have two masses, one of which is on the torsion balance, the other one we need to bring close to it. And then speak a bit about noise and systematic effects. If I've got time, describe as novel technique as well that we've got for measuring contact potential signals with essentially a control like measurements, which is very precise but specific. And then describe just what we're doing at the moment to actually. So yes, it's just the background of measuring gravity at short ranges. So I'm sure a lot of you have seen this sort of plot before, but essentially it's showing the region up here is a region of excluded space for a UCAL-like modification to gravity. And a good way of thinking of this plot is basically how well you can measure gravity at different ranges. So you can see at the range of a centimetre, you can measure it more or less to 1 part in 1,000 if you exclude an alpha of 10⁻⁵. If you look then at, say, a range of 1 micron, this is saying essentially we can't measure gravity at 1 micron. We can say that it's not become 100 million times bigger than it is on the scales. And yet these are sort of typically types of experiments that are used to do that. So torsion balance experiments and micro-cantilever experiments. And we're trying to develop something that will sort of combine some of the best features of those. So this is sort of an earlier version of the device, which is it's based on a superconducting levitation system, and it's the way this works essentially. It's quite simple. It's a ball and socket. So we have on here, on this hemisphere here, we have a spiral lead or niobium coil in which we put a persistent, store a persistent current, and that creates a magnetic field. And then you lower a float, which is also of a superconducting material. It traps the field. And so what you get is essentially, as the gap decreases, you get a magnetic energy density that goes as 1 over the gap, and then you have the gravitational energy which goes as the height of the gap. And so in between those you'll have a stable position at which it will oscillate, and this makes it a pretty stiff spring, so you can balance it there. It also holds it stiff translationally. One problem though, this version of it essentially, it's like a conventional torsion balance, it's still unstable with respect to tip and tilt, and sort of wobble because of its spherical structure. So that limits sort of the size of the areas you can bring close together. You have to have curved masses so that this mass can wobble past that mass. So we've come up with a new design which I'll show you sort of start the triangular thing for the inverse square law experiment, which is aiming to get into this sort of region of parameter space. And so yeah, the idea is to bring 2 flat masses close together. So we're trying to build something that that is essentially stiff in 5 out of 6 degrees of freedom, but we can still be sensitive in one rotational degree of freedom, as in a torsion balance. And because it's a superconducting experiment as well, this was all cryogenic, so it reduces thermal noise. In this case of Casimir, with the Casimir experiment, it will reduce thermal, the thermal Casimir force. This is the overall structure of the experiment. Essentially here, these two circles, those are where the test and source mass will be. We'll have one of those, one of those will be on the levitated on a superconducting bearing, which is now triangular rather than round, so that will be in the middle. I'll show you a picture of that in a moment. Another one positioned on an array of, by an array of micro positioners and adjusted until it's essentially, you levitate the bearing and you don't know exactly where it's going to be, so you measure the relative position and attitudes of them with the capacitance reads that bring them close together. And then you have an interferometer. Basically you actively rotate one of them and look for the periodic torque induced in the other one. So this is the prototype of the actual superconducting bearing. So what we have now is we have 12 coils in total rather than just the one. Each of those is spiral lead coils, racetrack coils, and each of those we can independently put whatever current we want in there, stored in a persistent current mode, and each of those is then facing a superconducting surface. So each of them essentially acts as an independent spring. We can tune the stiffness of each spring, so that these 3 coils by themselves will levitate it. They'll also make it stiff with respect to tip and tilt, but by themselves the float would just slip away sideways, so we put side panels on it. And I'll explain in a moment as well why we have 3 side coils on each side. Just one. This is the idea. Then when you cool it down, you lift the float, lower it onto inject current into the coils and then lower it onto the coils and it levitates. This is a science float. To actually get a sensible mass on there, we need to make it out of metal, and we chose copper because we made almost everything else out of copper. And you can see here, so the inside is coated in lead, the superconducting surface. The outside is coated in gold, and that's so that the outer surface can act as a mirror for an interferometric readout. Science from bearing, essentially we've increased the surface area of the top to make it more easy to levitate the float. So I mean that's a big limiting factor is the weight that we can levitate the float. We've got weighs about 40 grams, and that's close to the limit of theoretical limit of what we can levitate before we exceed the critical field of lead. So it's produced, this is actually aluminium, it's then anodized to make an insulating layer so that it won't short the coils, and then goes in a very thin layer of gold to remove charge. And yet the other coils are made in the same way. The little thing in the middle, that's and there's an atoll cube hiding inside it whose only job is to lift the float and then lower it onto the bearing. That can also be used to heat the float to near it. Okay, so this is so it's pretty, except the top coils will hold it stiff, and the side coils will. Between all those, they'll make it stiff with respect to tip, tilt, X, Y, Z. You could say, well, what about how do you make it soft with respect? How do you actually get it to rotate? So what happens there is the 3 different side coils we have on each surface, they act differently with respect to rotation. They all make it stiff with respect to translational motion. If we just had coils in the middle, and if you can imagine sort of pushing out on the box, it's unstable. If we just had these central coils, the thing would just rotate one way and stick, or rotate the other way, so it would fall rotationally. So if we just had these 2 outer side coils, that would hold it very stiff. And so by essentially balancing the stiffness of these different coils, we can tune it to be either stable or unstable, or give it a very long period. So what we want really is, because we you can choose the frequency of our torsion balance and of our signal, because we're actively just rotating the mass. We try and put it in the minimum of the measured seismic noise. Yeah, about that would be with rotational. So about 1 hertz. Those of you that have worked with torsion balancers would probably say, well, actually, what you've made there, if you made a soft rotational spring, it's still not torsion balance. There's a vital feature of a torsion balance is if you hang some test mass distribution of it from a point, then it will swing until the centre of mass of your test mass is below the point of suspension. And that's sort of part of the magic of how it works, because then when you shake the suspension point to go in, and seismic noise shakes the suspension point, you will only produce the first order translation of your torsion balance rather than the rotation. We've got rid of this tilt degree freedom, so now if we have a centre of mass offset, say in this direction, this is looking above it in plane, then a force in this direction will produce a torque in this direction. What we can do though is, we've got enough, because we've got so many coils on there, that we can adjust separately. We can adjust these to effectively, well, change the axis about which it wants to pivot so that it lies on top of the centre of mass. And we can actually do that to sort of in both axes independently of having already tuned the period. We've got enough freedom to do that. It's actually other sort of thing. So yeah, we've sort of built a model of flow dynamics and convinced ourselves that we can control the dynamics of the flow, so looking at them. Basically all the cross couplings between the modes, and seeing to try sort of test them how sensitive we are to geometric imperfections. So a lot of what we found is a lot of geometric imperfections, the first order will just act like a centre of mass offset, and we can cancel it in the same way. And this is our sort of noise budget for it. We think that the biggest noise source will still be residual coupling of the centre of mass to seismic noise. There are other limitations we have to we have a lot of tilt noise. We would then get the sort of gyroscopic effect would produce a random walk, and so we need to damp tilt modes. We need to not damp the rotation mode. Actually, that happens for free really, because we're using mainly eddy current damping proportional to frequency. Frequency squared, we have a high stiffness in the other modes of sort of tens of hertz and a very low frequency in the torsion balance mode. Finally, this is sort of, we've also developed an angular interferometer, which is what's actually looking at the surface of the float and telling us the position of it. And well, there's been a lot of work in actually getting that to work cryogenically, because it's fed by the PM5, which doesn't like to be cooled down. But we've got that now working at 4 Kelvin at seismic noise level, so at 0.05 hertz and below 1 nanoradian per hertz. You can just see behind there as well. So this is an actual source mass for our gravity signals, so I'll explain sort of what they look like now. So on the top it just looks like a gold surface, on the bottom it looks just like a copper surface. So what it actually is it's like this essentially. The way we've made this is upside down, the way a lot of people like to make these sorts of things. We started by coating a silicon wafer with gold, electrodeposited layers of this spoke pattern of gold and the radial spokes, and then infilled it with copper. There are also, I haven't shown it, but there are other layers to stop interdiffusion between the copper. That produces a density contrast, but shown in the upper surface, it should produce no electrostatic signal, because it just looks like a flat layer of gold. So the idea is to bring two of those together. So yeah, this is just manufacturing them. So if we have a better, I don't know if you could see that closely enough, you'd see 2048 sort of raised spokes of gold, and then this is after it's been infilled with copper. Then the big challenge is actually then we etch away the silicon. We then need to stick the thing on a support structure, and it can't be a big flat piece of metal because we can't levitate a big flat piece of metal, so it has to be a radius of it. It's one of the big difficulties we have in experiments. Yeah, so that's sort of the gravity experiment is just bringing two of those close together, facing each other, measuring the torque in between them as we rotate one with respect to the other. If we just left it like this, dipping in filler with copper, then essentially we've got the Casimir force experiment. We can just put those together, rotate one with respect to the other, and what we actually see then is we'd see a Casimir force signal about 10 to the 5 times bigger than the gravity signal that we're looking for. So we're suddenly less worried about getting all this sensitivity from the torsion balance. Then we have more difficulties in terms of electrostatics and flatness and so on, and how that will affect the signal. So yeah, this is sort of how it would work as a Casimir experiment. So now we actually have raised boats, so like in this schematic picture. We have two patterns like this facing each other, and the perfect conductors. We start with the usual equation for the energy, and then rather than differentiating it with respect to Z, differentiate it with respect to A. So we've now got two areas sliding past each other, or for each pair of spokes we've got sort of a change in area per unit length, distance in this direction equal to the length, and so that gives you the torque essentially value of this is the sort of the length of one stripe in this arrangement. This is its radial average position, so this is the Casimir torque that we need to observe. And yeah, so that means we've got another, I don't know if you call it an advantage, but we now have a sort of an inverse cube signal rather than an inverse fourth power signal. Actually is important because we can now work at a larger gap, and because because it's at 4 Kelvin, we've got thermal wavelength of 50 microns, and so we can work at sort of 5 to 10 microns if we want. Yeah, so this is the geometry. We've got sort of a photo mask, and we've got foils, and this would be a little a copper mirror that we've had some of those made for another reason, so we can etch this pattern into one into a copper mirror, one into a foil flat on the float, and then say this is our initial design. It's not as big a signal as we would get from the gold thing, but we can hope we can more easily bring these close together. And as I said, the limiting factor for this now becomes flatness and accuracy and precision of the masses, positioning of the masses. So that's the sort of thing. So the micro positioning system now becomes a more important challenge, so I'll just describe that. So what we've got is a total of 7 metal cubes, 8 if you count the one that lifts the foot. It's really part of this. So what we have is an XYZ positioner here, a rotational position there, which rotates the source mass to produce a periodic torque, the test mass. And then, rather than use a goniometer, which would then lead to a sort of wobble as we rotate it and so on, lack of reproducibility, what we use is 3 Z positioners to form a kinematic mount. So we lower this onto that. In fact, this picture is a bit dated. We now got an arrangement where we actually drop it on the kinematic mount, and it sort of stays there, so we're not pushing down on it. And yeah, so what we do then is we measure the usual thing for getting things parallel is we measure the capacitance, the absolute capacitance, the adjusted gap. We then actively tilt it over some range, look at the quadratic term, and go to the minimum quadratic term of the capacitance to find where they're level. Yes, just describing that. So also to censor it, we use we've got rods on the outside for the ISL test mass, which looked like a flat piece of gold. We've actually got little raised bits of gold in the middle to help with the alignment. The Casimir mass, we've got that built in, so we can just use the capacitance between the raised spokes for the alignment. We again, this is an important thing at the end though. The measurements are sensitive to flatness, so if you do this thing where you tilt it over some range and you curve that one edge, then or you've got the bit sticking up at one edge, then you'll get some offset. So we sort of modeled that and modeled its sensitivity to output flatness. This is just, we've got the usual sources of systematic torque. Yeah, we can use ferromagnetic materials. This is back for the ISL match. The reason we chose copper and gold is because their thermal expansion is so well matched. So one is 324 times 10 to the minus 5, one is 326 by 10 to the minus 5, that's 4 Kelvin. So that's the difference, that's 4 Kelvin. So that will produce a very tiny corrugation. Background magnetic fields will give sort of, because materials have different susceptibilities, that will produce a torque, but we don't have to. It's not a very stringent condition, but we have got magnetic shields on the Duet anyway. This was other things we thought of, so differential strain layers producing the contact potential difference, magnetic impurities and patch fields. These are some of the limitations that follow from that. So the contact potential difference, that's a sort of challenging one, that we need that to be less than 5 microvolts. That's between nominally flat gold spokes, so it's just if in some way the gold can see that it's on top of copper rather than on top of gold, that would become a major signal. The amplitudes of corrugations need to be less than 30 nanometers, or we get the bigger Casimir. This is a novel device. I'm showing you the sort of the physical thing first, just so that you can try and guess how it works, and then I'll explain. But this is to measure any contact potential difference between sort of an array of spokes, and it will also be sensitive to any patch field signal that's coherent over that length. So we expect obviously anything will have patch fields on, and we've got gold surface. What we're worried about is we're looking at 2048 pairs of stripes, and so we're worried about that will average out the patch fields to a pretty large extent. It's how much power is still left in the patch potential, that range. And this will measure some of that plus any actual contact potential difference. So we've made this thing, which this is a sort of maybe shows a bit more clearly what it does. So rather than essentially we've got the same pattern of stripes, but now one pair of them are all sort of connected to one electrode, another pair of them are connected to another electrode. And so what we can do is, as well as the usual thing of sort of applying the potential difference between your two masses, we can now apply a potential difference between an extra potential difference over one of the masses over a period. And what we get then is you get the usual sort of a torque that goes as the square of the total voltage difference. You also get so the total energy here would be sort of, if we've got contact potential sort of phi relative to in one thing, relative to 0 in the other, total energy is sort of V squared, V2 squared, V1 minus phi squared. If we then shift the periods along by one thing, we get potential of V1 squared, V2 minus phi squared. The difference between these things is now linear in the contact potential difference. So this phi represents either a periodic contact potential difference or just the residual contact potential difference from patch potentials not quite averaging out. So this is what we're doing now is actually transferring these foils. So once you etch it away, it looks like that, which actually took us a lot of work to get it. There's low stress in the foil that actually looks like that needs to be held up. then to transfer it so it's flat, what we have is we have a vacuum chuck with tiny holes on, so we put it down and it's flat. We don't just want it flat, we want a bit of tension in it. And so we come up with some devices to sort of tune the tension. So what we have in cross-section, the test mass holder looks like this. It's an L shape, goes round in a circle. And so we can bend it outwards while it's being glued onto the foil. Then when we remove this device, let it go, then it's sort of, so it's like that when it's being, like this when it's being glued. And we take it off, it's along here, let it go, then it pulls out like a drum. So what we're making is tiny copper drums. And we can then measure the flatness of those pins in the usual way, by scanning them and or something like that. And we can also measure the tension just by sort of flicking them and listening to the note that we get. And yeah, so we've done that. We can get things flat to a few microns, usually at the edge is where we get the biggest problem. And but in the central area we can get it to within 1 micron. So yeah, we've defined conclusions. We've sort of built this thing, which we think provides a unique platform for measurements. We've made the foils, we've sort of seen how we can position things as we want them, but we still need to fully characterise the levitation system and then actually put masses on the float and the source mass to do a science run.
Thank you, Chris.
How small angular deflections can one measure?
Sorry?
How small angular deflections is it possible to measure?
Okay, so at the frequency we're interested in, we can measure about just like about half a nanoradian. So at 0.05 hertz. At high frequencies it's more sensitive.
A nanoradian?
Yeah, a bit less than a nanoradian.
Oh,
yeah.
fantastic.
So, first of all, congratulations. It's really an amazing machine you've built there. I have actually a few questions. The first one is regarding the flatness. You mentioned that you can get these gold foils to 20 micrometer. So that basically also limits the distance range which you can approach.
Yeah, so that is the limiting factor at the moment. That's been the big problem for the inverse square Law experiment. So what we have is, if you look at, I think one of the early pictures I showed of see if I can find it, of a gold foil on a float. This is from a couple of years ago where we already had some methods for making this flat and under tension-ish, but it's sticking up a lot at the edge, and so we have edge problems essentially in gluing it down. We think this new technique where we bend the rim in a certain way, and glue it. If we bend it far enough and if we get the thing sitting on the chuck correctly, then it should actually, once we let go, bend the edge away from it. And we've modified it a bit so that we've got a sort of on each side a 1/4 of a millimetre overlap of the foil, so it should actually just sort of be like a drum and slide down. So we're just doing those transfers at the moment.
But the foil is one thing, but this also applies actually to the other side, where you have these edged surfaces with the corrugations inside.
Yeah, so what we're thinking is, so this is for a gold foil, but gold foil. The Casimir experiment, what we'd have is one of the masses would be easier to make the ping on the source mass, which would just be a copper mirror that we happen. The other one would just still be a foil, probably could make a gold coated copper foil or just a copper foil to start with. So we do exactly the same thing because we can't put something thick and flat on the float. We can't lift enough weight. We probably just put a foil and just use the middle area of it. Maybe that's what actually when I was talking about that.
Well, a typical semiconductor wafer, which is used for production, has a bore warp of 40 micrometer, but you can flatten that out. You can get it to approximately 2 micrometer over the whole range. So if you take such a wafer and then you pattern it and then you deposit gold, if you could get something which is way more flat.
Yeah, we could do so. We could, say, when I showed the prototype, it's like silica float, that was made out of optic flats, and was flat within, even sticking the rest of the stuff on, was flat within a couple of microns. So if you wanted to use gold, or dielectric, or just a gold coated dielectric,
Okay, I think we should end the session. Thanks, Chris, and all the speakers. And